Any queries, sir? Thank you, sir. Now I request Dr. R.R. Bhavani ma'am to thank our chief guest of day 3 of session 1 and introduce our session 2 chief guest. Ma'am, please.
Good evening, all. On behalf of all of us, I convey a sincere thanks to Dr. Narayana Prasad for his talk on high performance computing and its association with AI. Sir, it was a very detailed lecture, and we all had the opportunity of exploring high performance computing in depth. Thank you, sir, for sharing your time and knowledge on OpenMP also with us. And the explanation was very understandable and in exact manner. Thank you so much, sir.
Oh, thank you, madam. Thank you for the opportunity.
Thank you, sir. Thanks a lot. Now it's
Thank you, sir.
time
Thank you, sir.
for the Now it's time for me to introduce the resource person for this session to our participants. Today, amidst us, we have a young entrepreneur. As Mr. Prem Kumar is the founder of Merchant RMS in the year 2018, and presently, Techie is around since 2019. Mr. Prem completed his BE in CSC from Dr. Shivandi Ayatnar College of Engineering in the year 2010. Initially, he worked in Smack Coders as senior tech lead from 2013 to 2015 and as software architect in Tendercuts.in from 2015 to 2018. He has a wide expertise in building commercial online stores, developing commercial applications, and automating business processes. Now I request Mr. Prem to start his lecture. Please, Prem.
Thank you, ma'am. Thanks for your detailed introduction. So, good evening to everyone, and thanks for this opportunity. So, I really feel honored to be part of this program as a resource person for today's session on edge computing. I'm just looking how to share my screen. May I know if my screen is visible?
Yes, sir.
Yes, sir. It's fine. Edge computing introduction.
Okay. So the topic is edge computing, as we all know. And this is an emerging technology that is like coming up. I believe there should be a subject for edge computing in current syllabus of Anna University. So this is a game-changing concept that is shaping the way we process and analyze data in real time. So in today's session, we will explore what is edge computing and how it works and some use cases of edge computing. You can see the slides, right?
Yes, sir.
Okay. So edge computing is a distributed computing. That means we can have multiple processors to process, to do the computations. And so far, people used to transfer the data to a cloud where they will do the process, and whatever output that they are getting from the cloud server, they used to display that in the client machine. But edge computing slightly differs. So they do the computation internally. They don't transfer the data to cloud. They have multiple processors to do the computations, and they display the data or whatever the response is, they display it in at client level. They do not rely on cloud, which means They save on bandwidth, they save on latency. So let me move on to the next slide. It almost mimics the public cloud platform, which means every capability of a cloud platform that can be done internally in the edge computing. So that is how it distributes the data. That is how it does the computation genuinely. Like it distributes each process and do that in an internal network. It does not transfer the data to a cloud. So thereby they reduce the delay that is associated in sending the data to cloud. So this is what we call as latency. So the reliability will be enhanced thereby, because if there is any network issue or if there is any bandwidth issue, that won't stop the process. So these are the building blocks of edge computing. It starts from data ingestion. So this collects and transfers the data from various sources to edge for processing. For example, these are the input devices like sensors. Let's maybe in upcoming slides we will have real case scenario. So by there I will be explaining more in detail. So data ingestion is simply the input for edge computing, like whatever data that is read in a sensor, that can be considered as data ingestion. Followed by the next thing is M2M brokers, where the communication takes place. Whatever data that we get from the sensors, that is transferred to the processor to M2M broker. So one protocol that comes under M2M broker is called MQTT. That is a highly known protocol. It's like HTTP for web computing. MQTT is a IoT protocol. So followed by whatever data that is got from the data ingestion, that is from sensors or any input devices, it can be stored. It can be either stored in a structured way by maintaining a database, or it can be stored without any structure called NoSQL. So function as a service is the next block, which is whatever inputs that we get, the computing takes place in this place. Next step is stream processing. This is the output, like whatever input that we have received from data ingestion through M2M, that is computed, and whatever result that we are going to, that is whatever action or any activity that we are going to perform based on the inputs, will be done in this stream processing. So this is a little bit more description about data ingestion. So this can be, as I told you, this can be a sensor in real time tracking a temperature of a machine to ensure it does not overheat. So just think of any industry machine which runs all time. So we have a sensor here in place to monitor its temperature. Let's say if the machine overheats, maybe the output should be the processor, that is the edge computing processor may switch on the cooling activities, or it can stop the machine to prevent side effects or after effect of this overheat issue. So data ingestion basically streams the data from IoT devices for immediate computation or decision making at the edge. So this is actually not an example. This is what the example is. This is like explaining the process. So next thing is machine to machine broker. So after we got the input, this is like a protocol which transfers the data. Whatever input that we get from the sensors, that should be moved to a processor to do the computation. So machine to machine, this does that activity. So this can be considered as a post office that receives messages from one device, processes them, and delivers them to the intended receipt. So after computation, the delivery will also happen through this protocol only. So this slide explains the example of M2M brokers. So when a machine detects a critical issue like overheating, it sends a message via M2M broker to a nearby cooling system for maintenance. This M2M broker processes this message and routes it to the relevant system, ensuring immediate action such as reducing the machine speed or activating cooling mechanism. So all this happens locally at the edge without relying on a cloud-based communication, ensuring low latency and preventing the downtime. So object storage is the next block of edge computing where the data is stored. So data ingestion, here we discussed about the sensor. In some cases, camera, camera can be a data ingestion, and the input that we get from camera can be a video file, which is not a structured way of data. So that is an unstructured data which can be stored on a hard disk or something like that. So in the next step, we will do the computation like analyzing the whatever video that is recorded on the camera and doing the necessary activities based on that input. So object storage is a way to store and manage data as individual units rather than files or blocks. Each object contains the data itself, metadata, and a unique identifier. So unique identifier we can consider as a timestamp. So when a video is getting recorded, usually a timestamp will also be there on the video. So that can be considered as a identifier. So this slide shows example of a object storage. So in this example, you can see a CCTV camera has been set up in a shopping mall, which is connected to one edge computing device with object storage. So this camera is recording the video, and if there is any activity of using AI or motion detection algorithm, if there is any activity of human, then that particular clip will be stored in the object storage. So thereby, this reduces the effort of monitoring the whole video or something like that. So that will be recorded against timestamp, which can be used as an identifier, location, and details. So the next slide is function as a service, where so this is where the computation happens. So this takes the responsibility of computing. If you want to do more sophisticated, you could actually move that to a function as a service. So for example, if you have a business intelligence in place, like the previous example, if there is a human movement in the CCTV camera, that particular footage will be recorded. That is what this computation will take care of. So the next block is okay. This is an example for functional as a service. So a smart parking lot uses edge devices to manage parking spaces and assist drivers in finding available spots. A vehicle enters the parking lot, sensors detect the car and send an event to the edge computing system. A function is triggered to check the current availability of parking spaces using real-time data from sensors installed in each spot. So another function runs to guide the driver by activating digital signs or sending directions to their smartphone. So may I know if you have any questions so far what I am going through? If anyone have any questions? Okay, let me move on to the next slide. So stream processing in edge computing involves the real-time analysis and processing of continuous data streams generated by devices like sensors, cameras, or IoT equipment. Instead of storing the data first, stream processing analyzes it on the fly as it is produced, enabling immediate insights and actions. This approach is critical for time-sensitive applications where delays in data analysis can lead to missed opportunities or risks such as equipment failure or safety hazards. So here is an example for stream processing where a smart city deploys a cameras and sensors at intersections to monitor traffic flow and detect incidents like congestion and accidents in real time. So traffic cameras. So usually there will be a traffic police in a place to monitor the number of vehicles, to monitor the density of density means the number of vehicles transferring through that place, and they will have to adjust the seconds of green signal manually. So through this process, this system can detect the number of vehicles passing through that place and set the seconds automatically. So here this algorithm detects if there is an increasing value in the number of vehicles, and based on that, this will increase or decrease the number of seconds green signal should be. So next thing is machine learning. So far, machine learning was well established in cloud computing when compared to edge computing. It is new to edge computing here. As in yesterday's session, we have been discussing about devices supporting AIs. So any device that is supporting AI that can be used in edge computing to do the machine learning. These applications have capabilities that is available in public cloud, but these all come to as the last mile delivery point and run very close to the source of these capabilities or brought into the edge. So as I told you, the devices means the sensors which generate the data and actuator which consume the data. Both of them are called devices. And if this computation is very close, that means this can do the capabilities of a cloud application. So if we have a device in place for machine learning, edge computing can do whatever that cloud computing can do. So since we are having machine learning internally in edge computing, this reduces latency and the bandwidth usage. So here is an example for machine learning model. A smart home system with energy saving feature uses sensors to track electricity consumption across various devices. Smart meters and IoT sensors measure energy consumption in real time. An ML model on the edge analyzes the data to predict patterns such as inefficient usage or applications running unnecessarily. The system can automatically adjust settings such as dimming lights or turning off unused devices to optimize energy use and reduce cost. So ADAS, this is the latest technology which is getting introduced in automobile industry. So most cars that is built by that is built recently is having this ADAS technology. So edge computing plays a major role in this new technology. So this is a real-time scenario. This might sound something interesting for a few of you because this sounds interesting to me. So this is an intelligent technology that is integrated into vehicles to assist the driver. So this technology is built to assist the driver. Basically, they provide adaptive cruise control, parking assistance, and traffic sign recognition, speed control recognition. So if there is a signboard that shows that speed control should be 80, this ADAS technology will not allow the driver to go more than 80. So when the vehicle is in ADAS mode, the vehicle keeps speeding at 80 km per hour speed. So these are the features of this latest technology. So traffic assistant, adaptive cruise control, lane keep assist, lane departure warning, electromechanical steering, parking assist, park help, reverse assist, night vision assist, adaptive lighting system, traffic sign recognition, so lidar, position acquisition, local mapping. So as we discussed the blocks in edge computing, data ingestion is the first block. So in this scenario also we have a few examples of data ingestion applied here, like camera, radar, lidar, ultrasonic sensors. So these are the input devices for this edge compute. So cameras can be used for object detection, lane tracking, and traffic sign recognition. Basically, camera is used for traffic sign recognition only here. Radar is used for doing these things. Lidar is used for detecting any object in the pathway. So radar is used for distance computations. speed computations and direction of objects around the vehicle. So this radar is used in this particular feature, adaptive cruise control and collision avoidance. So this is where this is the main technology that is implemented. This is the main input source that is implemented for ADAS. This is one of the main thing. So this provides a 3D mapping of the environment using laser pulses. So it is like a light which is not visible. So when you pass a light in the pathway, if there is an object, light will not travel. So this is something similar to that. So they do a 3D mapping as like passing a light, and then by therefore they deduct if there is any obstacle, and based on that they do these calculations. So next thing is ultrasonic sensor, which is an ancient technique. It's kind of an ancient technology. So this ultrasonic sensor, this can be used to detect if there is any. This is a this can also be used to detect the obstacles, but LiDAR is the latest technology. So this ultrasonic sensors is almost used uh, when when parking or when using the reverse gear. Ultrasonic sensors are used. So after data ingestion, the next thing is M2M broker. So the inputs that we get from a data ingestion is transferred to M2M broker, is transferred to ECM. ECM is a processor which does the functional FAS. So ECM gets the input through M2M. So this M2M transfer the data from the sensors that we just we have just seen. So this enables transferring data real time between the vehicle components, its infra, and sometimes if needed, it will transfer the data to external systems also, like the latest admiration in automobile industry is that Tesla car, which communicates with external systems. So one car will communicate with one vehicle will communicate with a nearby vehicle. So this also comes under edge computing only, and it can also be considered as cloud. But without transferring the data to cloud, it is transferred to the nearby vehicle, so it should be considered as edge computing. So this communication actually enhances the safety, efficiency, and performance of the vehicle by allowing the systems to make autonomous decisions based on the information from data ingestion sensors. So whatever information that we get from data ingestion, based on that, it can assist the driver. So this technology relies heavily on the sensors that we just discussed, and followed by this M2M, where to exchange the data. This transfers the data to CPU. In vehicle, it is called as ECU, and a radar sensor may send information to vehicle's braking system, signaling the need for braking automatically if an obstacle is detected. So vehicle to vehicle also it transfers data. M2M allows to connect with the nearby vehicle. So maybe it will maybe it will transfer the speed of the travel. So based on that, the other vehicle adjust itself. So this seamless flow of data between this multiple sources, that is between the sensors to external system, which can be referred to next or nearby vehicle, or to the ECU. This can make, this can help decide, this can help to make an autonomous decisions. So through M2M, ADS can monitor the vehicle's internal system for any potential issue and predict when a maintenance is needed. Sometimes the system will itself detect if there is any issues with the sensors inside the vehicle, such as monitoring the tire pressure, engine performance, and a braking system, which can alert the driver for scheduling a maintenance before a failure occurs. So in adaptive cruise control, M2M communication between the front facing cameras, radar sensors, and the braking system enables the vehicle to detect potential collisions. So this is an example of transferring data to a nearby vehicle. If the system determines a collision is nearing, or if there is any obstacle, it will automatically apply the brakes to prevent or reduce the severity of the accident. So next thing is parking assistance. M2M enables the sensors in the front and rear bumpers to communicate with the steering system of the vehicle and braking system of the vehicle, allowing the car to automatically park itself by controlling or adjusting the speed into the parking space. Apart from this, okay, so the next thing is functional as a service in ADA. So ECU is it's a kind of processor. So there will be multiple ECUs in a vehicle. So this is called as electronic control unit. The simple form is ECU. So once the data from ingestion is transferred through M2 ECU, now ECU decides what action to be performed based on the data that it has received. ECU processes the data that is received from data ingestion sensors like radar, cameras, or lidar, whatever that we discussed earlier, to make the a real-time decision. So this is where edge computing comes into the place. This, since there is no latency, since there is no need of transferring the data to cloud, this can make real-time decisions quickly that assist the driver and improve the uh, comfort of driving, or something like safety of the vehicle. So there will be multiple ECUs, and each ECU will have a specific task. Like a braking will have a braking system will have an ECU, a steering system will have an ECU, an adaptive cruise control system will have an ECU. So ECUs are responsible for interpreting the data that it got from the sensor, and it takes a responsibility of making decisions on controlling the vehicle by the way it assists the driver. So to explain with an example, here is adaptive cruise control. So sensors detect the change in the speed of the vehicle agar. So this control the actuators. So ECU makes the decision. It sends the command to the vehicle's actuator to perform an action. So based on that, these actuators will control the components like brakes, steering, or throttle. So let's say if the ahead vehicle is increasing its speed, this actuator will control the throttle to increase its speed and it will keep following the vehicle. Maybe if the ahead vehicle is braking, the actuator will engage brake to slow down and still it will keep a safe distance to follow the same vehicle. So these ACUs has the capacity to transfer data through M2M to a nearby vehicle. For example, the ECU that controls the lane keeping assist system will communicate with the ECU that manages the steering to adjust the steering angle if the to move the vehicle from one lane to shift the vehicle from one lane to other. So here the redundancy of data is very crucial because vehicles often include, as I told you before, multiple ECUs for the same system to ensure that if one fails, another can take over. So this enhances the reliability and the safety of the vehicle, which is extremely important in semi-autonomous driving system or in autonomous driving system. So there are a few types of ECU that we have not discussed yet, and that has not been added into the slide. So few of them are radar ECU, which control the radar sensors, use the system like adaptive cruise control and collision warning system. Camera ECU, which helps to monitor the road environment and traffic signs. So if there is a sign in the traffic from the traffic department, this camera detects it and take necessary action based on it. So LiDAR ECU, which will be used in the automated parking assist. As we discussed earlier, braking and steering, I think we have discussed that. Central gateway ECU. This is the central communication hub between all ECUs in the vehicle, ensuring smooth data exchange across the system. So to simplify this, ECU work in harmony, each focusing on different vehicle functions while sharing the data to enhance safety and driving comfort. So the main advantage of using edge computing in this ADAS is the real-time response. So ECU process the data from sensors almost instantly, enabling real-time decision making. So that is the main advantage of edge computing in this ADAS technology. So comparing edge computing with cloud, edge computing is emerging recently. Cloud is there. Cloud has been there for the past 10-15 years. So anything is possible in cloud, whereas edge will have some limitations. So So these both are key technologies that is in place as of we are in 2024. So they differ in terms of processing the data, uh, comparing latency of both the systems. Edge does better. So in simple terms, edge computing is something that computation will take place too close to us, where the system is in place. Whereas in cloud computing, the data will transfer to a centralized server that can be miles apart, and whatever response that we get from this cloud computing, that can be used in the real-time exam. So in cloud, the servers, storage machines, databases, everything will be over the internet. So data will be sent to the cloud where it is processed and stored. Whereas in edge computing, data will be processed locally. So considering latency, as we discussed, winner will be the edge, because in cloud, the data has to travel place to place. So data has to travel to the cloud and back, introducing significant latency, whereas in edge, the data will be processed locally. So ensuring that ultra low latency. So edge is the winner when it comes when latency is in place. Connectivity dependence, again, edge will be the winner because cloud requires a stable internet connection to transfer data between.
Prem, you're muted.
Hello.
Yes, sir.
Yeah, it's now it's audible now.
May I know from which slide I have muted myself?
Just from the previous slide.
Okay, from computational load, right? So computational load, let me repeat again. Centralized server can handle heavy computational tasks, making it suitable for large-scale analytics and training AI models. Whereas in edge, we will have different processes to do it own to do it own to do its own computation. So cloud is the winner for computational load. So coming to scalability, cloud is easily scalable. Adding more and more resources, adding more and more server is feasible when we go with cloud. But in edge, it's limited. Hardware constraints are there, so it's limited. Casting. So for the setting up for setting up a cloud versus setting up an edge, cloud is cheaper because edge comes with, we will have to incur for hardware also, whereas in cloud this will come as a service, so initial setting up fee will not be there. But for long term, edge is considered because cloud is billable maybe cloud is billable based on the time period, maybe monthly or maybe an yearly. But edge, if we have invested one time, then it should do its work. So considering commercial factors, edge is the winner. And thanks for the opportunity. And any questions, I'm here to answer it.
Participants, any queries? Thank you, Prem sir. Now I hand over the session to Mrs. Muthu Poochend Radha ma'am. Ma'am, please. Good evening, everyone. I am privileged to extend a sincere vote of thanks to all those who contributed to making the third day of our faculty development program a great success. First and foremost, I would like to express our deep gratitude to our esteemed speaker, Mr. Prem Kumar, team lead, techies around Chennai, for taking the time to share their valuable expertise with us this evening. Our insightful presentation have been both enlightening and inspiring, and we are sure they will have a lasting impact on our teaching and learning practices. A heartfelt thanks to all participants for being with us today from 6 to 9 p.m. Your active participation, engagement have added immense value to today's session. Finally, a big thank to everyone present today for making this event a success. We look forward to your continued participation in the upcoming sessions and hope that you take away a wealth of knowledge to apply in your professional journeys. Thank you once again. Thank you.
Participants are requested to fill the feedback form.